Good evening, everyone. My name is Seda Said, and this is our 10th interactive session class. Today, talking about, we will be doing some questions on settlements in pile foundations and pile groups, which we have studied in 10th and ninth week. So, let us get on with that. Uh, So the first question is for the settlement in pile foundation because last week we did a question on the excuse me pile capacity. Today we are going to do a question on the settlement on in pile foundations. So we know that as we have studied in class also, we know that there are three kinds of settlements in piles. We take total settlement is equivalent to S1, E1, let's write E for this. So E1 is the elastic settlement of the pile material. For example, if it is concrete, then if this is our pile, there is going to be some settlement in the material itself. Then E2 is settlement at the end point, um, settlement at tip of pile, and then E3 is settlement along the shaft due to the friction. Okay, so because we are running almost 1 week late, so what I will be going through some questions, and I'll not be elaborating it as much as I usually do because it is everything that you have already studied in the you've already studied this in the lectures. Okay, so the first question is allowable working load on a pre-stressed concrete pile is 21, which is 21-meter long, is that has been driven into sand is 502 kilonewton. The pile is octagonal in shape with a diameter of 356 mm. Let me remove this. We don't need this here. Skin resistance carries 350 kilonewton of the allowable load, and point bearing carries the rest. Use elastic modulus of 21 into 10 to power 6 kilonewton per meter square, and uh, soil modulus of 25 into 10 to power 3 kilonewton per meter square, and Poisson's ratio of 0.35. I can and a chi of uh, and a zeta of 0.62. So we need to determine the settlement. So let us get into it. You know that SE1, the S1 that I was talking about. So we know S equals S1 plus S2 plus S3. For S1, we calculate working load as zeta times sorry, this is S. So this is on the pile tip, and this is at the pile tip, and this is along the shaft. So first, let us calculate the AP and the EP. Actually, we don't need to calculate it as such. When we are using precast concrete piles, usually we take there are usually only two cross sections that we take. One is a square cross section. It's not exactly like this. It looks something like this. For square, and then we have an octagonal shape also, and there are these tables in which you will get the idea about their section modulus and everything. So for now, we don't need to calculate it. I will just provide you with the information on the elastic modulus as well as the area of this particular section, octagonal se octagonal section with a diameter of 356 mm. So for that we have an area 1045 centimeter square. It will have a perimeter of 1.16 meter, 1.168 meter. EP is given to us. ES is also given to us. So let us calculate then. Our QWP is 350 kilonewton. So our SE1 will be equivalent to, sorry, we have been given QWS actually, the skin resistance. This is QWS. And QW is given 502 kilonewton. Therefore, our QWP will be, so actually working load is equivalent to the load carried by the pile shaft, working load carried by the pile shaft plus the pile tip. So our QWP will be equivalent to 502 minus 530, which will be 152 kilonewton. Now our SE1 will be QWP 152 plus zeta times QWS, which is 350, times length, which is 21, divided by AP. This will be equivalent to 1.0. This will be 1045 into 10 to the power minus 4 meter. So we can write here 0.145 into the perimeter into length. No, not the perimeter, into EP. So let's calculate this. SE1 comes out to be 3.35 mm. So let's calculate SE2 now. This is 1. See, all these are happening in the soil material itself, on in the concrete material or whatever material of pile you have, because you see we are not talking about any of the properties of the soil. I mistakenly said the soil elastic modulus previously, because it just skipped my mind at that time. But this is along the shaft, and this will be at the end. So this is basically settlement of the pile material itself, all the three. So SE2 is QWD into 1 minus square times IWP. So this will come out to be QWP will be QW, this will be QWP by A. So it will be 152 over 0.145 into the dia, which is 0.356, divided by the ES, 25 into 10 to the power 3 into 1 minus, okay, there is a typo here. This is actually, okay, this is 0.35 square, and this has to be multiplied with the influence factor for the pile tip, which so IWP for S2 is approximately equivalent to 0.85. So here we take 0.85. Let's calculate SE2. This comes out to be 15.5 mm. Let us take now S3 due to the shaft friction. The equation is almost same like for the pile, but the influence factor is a little different, and that was divided by area. This will be divided by the shaft area, not the end area. So in this case, IWS will be equal to 15. Let's calculate this. So this was given by Vesic, and this comes out to be 4.69. So our S3 will be 350 over perimeter we had mentioned in last slide. Let's calculate this. This comes out to be, so the total elastic settlement will be 19.69 mm. So that is the answer for this question. So let's move on to the next question. A section of 3 into 4 pile group pile in a layered saturated clay is shown in figure. The piles are square in cross section, 14-inch into 14-inch, and center to center. Excuse me. Center to center spacing D is 35-inch. Determine the allowable bearing capacity of the pile group. Use a factor of safety of 4. Note that the groundwater table coincides with the ground surface. Okay, so let's start with this example. As you know that summation of the we know that there are two ways in which this group of piles can fail. It can either fail in n times Qu, where n is the number of piles and Qu is the failure load of one pile, or as a block. So it can be a block failure in which the whole block is taken as one entity and we calculate the bearing failure here and the friction load capacity here, the bearing load capacity here, or we can take one pile uh, and calculate its total failure load, multiply it by the number of piles. So whichever is lower of the two, that will be the strength, because obviously because if this is lower, then if Qn is lower than Qg, till Qg is reached, the pile group will have failed due to the NQU load, and if Qg is is lower than n times Qu, by the time n times Qu is reached, the whole pile group will have failed in block failure. So let's calculate the capacity, pile capacity here. So for the top layer, our QU, sorry, the CU is 1050. Let's call this CU1. And the bottom layer, the CU2. This is pound per feet square. This is 1775 pounds per feet square. So for this, our so let's do one thing. Let us calculate the capacity of a single pile first. Let me erase this. So our QU equals QPU plus QSU. This is due to end bearing and this is due to friction. And for clay soils, because last class we only did sandy soils, uh, that is why, sorry, I need to write soil. Uh, so we did not discuss the clay soil. In clay soils where phi equals 0, as we had mentioned, our end bearing capacity is CNC plus Q NQ plus half of B gamma and gamma, and this we ignore in piles, and for phi is equivalent to 0, NQ equals 0 and N gamma equals 9. So we take the QU, P equals 9 times C U, and then we take QUS. So there are a number of methods that can be used to calculate. If you remember, in last class we discussed that the it will be the unit friction resistance multiplied by the perimeter multiplied by the length. So basically, this is the uh, curved surface area or the surface area of shaft. This is surface area of shaft. So this F we calculated in sandy soil. We calculated it as uh, F was taken as sigma times Kv tan delta in sands. In clays, we have an alpha method of calculation, beta method of calculation, and gamma method of calculation of this F. I will not go into the detail of these methods, but what I will do is I will provide you with F for this region and F for this region using the alpha method. So F1 will be equal to, let's call it alpha 1. This will be equal to, there are charts for this in the alpha method, and alpha 2 or F2 will be equal to okay. So let's continue. So our QU equals QUP plus QUS. QUP is equivalent to 9 times C, but out of these two, we have to take this C because the piles are ending in this clay. So the C we will be taking is 1775, and QUS will be okay. This will be multiplied by the area of pile, and QUS will be alpha 1 into the perimeter of the single pile multiplied by the L1 length plus alpha 2 into P into L2. So QUP will be equal to 9 into 1775 multiplied by 14 inch into 14 inch. So it will be 14 square, and QUS will be equivalent to 0.595 multiplied by the perimeter will be 4 times 14. L1 is 15 plus 0.51 times the perimeter. L2 is 45. Let us calculate this. So we know that see L we are taking in feet and this we are taking in inch. We know that 1 inch is equal to 1 by 12 feet. So we need to divide this by 12 everywhere. So this is whole multiplied, whole square. This will be 21743.75. This will be 148.75 and the total QUP will be equal to oh uh, I missed a point here. This was 0.592. Actually, F1 equals alpha 1 times CU1, where alpha 1 is 0.592 and F2 is equivalent to alpha times Cu2 and alpha 2 is 0.51. So I need to modify these multiplied by C1, which is 1050 and this is 1775. So I need to multiply here also. I skipped this. Okay, I need to correct this. This will be 233835 and the total will be have to write. So this will be in pound, and will be 255.58 kilo pound. And then our pile group capacity will be equivalent to n times number of pile times qp qu. That's right. This will be equivalent to number of piles are 3 into 4. This will be equal to 3066 kilo pound. So this is the capacity of the pile group based on a single pile. Let's calculate the capacity based on block failure. Actually, here let me write uh, instead of capacity of single pile, let me write uh, pile group capacity based on single pile failure. Okay. So for the group pile, what we will have is the pile group will be something like this. And this will be our bread. Okay. Center to center distance is given as 35, I think. Yeah, 35 inch. So let this be LG and let this be BG. So our LG will be equal to, this is 1, 2, 3. 3 times D plus the pile diameter because of the half radius here. and half radius here, and then our VG, actually it will be n minus 1. So let me write 4 minus 1, and here it will be 3 minus 1 into D plus T. This will be 4 minus 1 times 35 plus the pile diameter is 14. 119 inch, approximately equal to 9.9, approximately equal to 10 feet. This is 84 inch, approximately equal to, not approximately, actually equal to 7 feet. So let us now see this block of 12 piles as a single pile, and now try to calculate its capacity based on the same principles we used in the previous slide. So our Qg will be equivalent to Qpg plus Qsg. This will be equal to here you see that we have to use a modified NC. This is still the same thing when we were calculating, excuse me, CNC, but some groups, some references have taken this this NC same as 9 times C, but in BM Das, a table has a chart has been provided for the value of N star, we can say CNC star here. So it is a bit different than 9. Uh, it's not exactly same. So let's do that. So this will be CNC into area of group, NC star, let me write, plus perimeter multiplied by length multiplied by C multiplied by, this is CU is taken as unit friction here. Let me cross check. Yes, CU is taken as unit friction and perimeter into length. This will give you the QSG. So the NC star in this case is, excuse me, sorry, excuse me. So our NC star will be equal to 8.75. So our group capacity will be, this is 1050 into 8.75 multiplied by our I'm taking this as 119 by 12 and I'm taking this as 7 itself so that I don't have to divide again. Plus the perimeter will be 2 times L plus B into length. Actually, it will be divided into two parts. This will be L1 is 15, 1050, 1775. So this will be 15 into 1050 plus 45 into 1775. Let me calculate. And then I will divide by 1000 to change into kilo because we will get in pounds. Oh, this is 1775 because that is the CU for the lower layer. So this comes out to be 4313.44 kilopound, and on comparison with previous 3066. So we can say that QG is equivalent to lower of 3066 kilopound or 4313 kilopound. So 3066 we will take, and our Q allowable will be equivalent to 3066 over factor of safety. I think it was 4, which will be equal to 766.5 kilopound. I want to mention here that some of the students get a little disturbed when we are not using the MKS system of units. This is the metric system of units, but in many cases you will find that even in field consultancy agents, they use feet and inch for not pound, as per they will use kg, but sometimes they use feet and inch for the length measurements. So not to get overwhelmed by a different kind of metric system. Everything else is same. It's just that there is a particular conversion constant between these systems. Rest, nothing else changes. Okay, so that was about our pile group, pile capacity in a pile group. Now let us take this question is about elastic settlement of pile group. So in this case, what we will do is what we did in the first question, this pile itself, but instead of one pile, there is a pile group of the same pile. Consider a 3 into 4 group of pre-stressed concrete piles, each 21-meter long in a sand layer. Details of each pile and the sand are similar to that described in question 1. So let us take these properties from here. Let me merge these two questions. So the allowable working load is 502. The pile is octagonal in shape. Uh, Diameter is given. Skin resistance carries. Okay. So we need to determine the elastic settlement of the pile group. Okay. So let us do that now. So in general, the settlement of group of pile under similar working load per pile is directly proportional to the width of the pile group. So there is not much to it. You just need to know that the settlement in the pile group is related to the settlement of single pile through this. You see, as I was saying, the settlement in the group is directly proportional to our BG. So as the breadth of the group increases, our uh, settlement in the pile group, elastic settlement in the pile group will increase. So the SE in question 1 was 19.69. So we know that if you get this question for a pile group elastic settlement, all you have to do is follow the same procedure as in question 1. Uh, we calculate the SE using SE equals S1 plus S2 plus S3, and then we correlate it with the um, file group dimensions. So our SE of group will be equal to square root of uh, we have to calculate the B. This is a 3 into 4 group. D by D is 3. So D by D is 3, and we know the D. So we will get D equals 3 into D equals 3 into 356. Let's calculate this. This is equivalent to 1068 mm. And our BG, let's calculate the BG first. This will be 4 minus 1. As it is directly proportional, we will be taking the longer side because it is always better to be on the safer side. If we are assuming more settlement, taking 3 would give us a lower BG, and which will give us a lower settlement. It's always good to be conservative than to face failure in field. So we will be taking the larger of the two into 1068 plus 356. So our BG equals 3560. I stand corrected. Sorry for the confusion. BG here is along this only. This is LG, and this will be 3 minus 1. I stand corrected here. That was my rationale, but this is how it is done in the text. So this will be 2492, and our SEG will be 356, and this will be equal to, this will be our settlement for the final group, elastic settlement. Okay, so in piles there is just one more question to deal with, which is the um, consolidation settlement in pile groups, and we will be dealing with it in after a short break. Okay, so this is the question about our consolidation settlement in clayey soil. So all the data about the layers has been provided in the figure. Let me resize it a bit. So, okay, let us go over the steps you have to take, you have to follow when calculating the consolidation settlement in pile groups. You see, in pile, it is still quite similar to what we do in shallow foundations. See, why we are taking, you see, if we're not talking about consolidation settlement in piles, because the area of this pile is too small to cause consolidation. What it can do is it can cause a punching kind of thing, but it will not cause a uniform settlement in a layer as such. Where what we are talking about here is that if we have a pile group which has a good uh, depth, a breadth, like significant breadth. This is the pile cap. So it will uh, act as a raft, and then below this settlement will take place, quite similar to what we do in shallow foundations. But the only thing is that we assume that the load transfer is being uh, starts at about 2L by 3 length of the pile. Where should I write this? I don't want to. So let's go over the steps. So the step one is that we need to know the total load. If the pile cap is above ground surface, then the load on the pile group will be equivalent to the load of superstructure. If it is below ground level, as in this case, Qg will be load on superstructure minus the weight of excavated soil. Okay, so now we have, for example, we have identified the load on the uh, pile group. Now, what will be the step two? The step two is that we assume load is transmitted to soil beginning at a depth of 2 by 3 L. So from here, 2 by 3 L, we see that the load is getting transmitted and we see the distribution of load. So the load will spread out one two vertical is equivalent to one horizontal. Two vertical equals one horizontal. So what we do is calculate the stress at mid height of, see in this question we have three layers of clay, one, two, three. So we have to calculate here, here, and here. We know the Q and we just need to know the area here, and then we divide the load by this area, that will be the stress here. You see, this two vertical is to one horizontal is in both directions. Okay, so next step is uh, delta G, or delta at height, will be equivalent to Qg over Bg plus Zi into Lg plus Zi. As I mentioned that it will like spread in horizontal as well as, uh, let me draw it here. will be something like this. So the spread is in both directions. This will be BG, ZI, LG, ZI. So after calculating this, okay, after calculating this, we will calculate the settlement at each layer. We know that settlement is C uh, H by 1 plus E naught log delta sigma plus delta sigma over sigma. Here it is mentioned in the question that all the soils are normally consolidated. So, as we had done for the shallow foundation, you know that if the soil is over consolidated, so you will take the shrinkage coefficient, swelling shrinking coefficient, and for normally consolidated, we take CC. And we also talked about a case in which we have a sigma which is NC, but sigma plus delta sigma is OC. So in for the NC range, you will take CC, and for sigma plus delta sigma, you will take CR. So we have talked about this. So now let us try, and then our total settlement will be just the sum of settlement in all the layers. So now let us do one thing. Let us start with the question. It will become clearer as we proceed in the question. So length of each pile is 15 meter. So the stress distribution will start at 10 meter. Okay. So the stress distribution will start from here. Now let's identify the layers. In the first layer, this is 16 meters. So at about 8 meter, we will have. See, in this question, QG directly is given, I think. Uh, Let me check. Yes, QG is directly given. If QG was not given and only the load was given, we would have subtracted the excavated weight of the soil. Okay, so somewhere at, let me draw actually the midpoints of the layers. me use another color. It's a little not that much visible. Okay, so these are the midpoints. Excuse me. You see, if this length, if the load distribution, if the load distribution was starting from here, then for the and the midpoint of the first layer was here, then we would have taken sigma for the first layer, simply Q divided by area or BGLG, because here Z would have been 0. It does not mean that there is no load here. There is a load here, but the distribution starts here. So for layer 1, this will be equivalent to, let's calculate, yeah, Zi, Z1 we can say. This will be equivalent to uh, here. It's only this much. If this is 10, and this is 9, I think there is something wrong with the scale of this figure, because we will have a midpoint. This is 9 plus 9, 10, 11, 12, 13, 14, 15, 16. We will have a midpoint at 8 meter, which will be above, but in this figure, uh, it is not seeming as the midpoint, but this will be the midpoint at 8 meter. So our delta sigma, the Vg is for this pile is the Vg given? Yes. So from here, if we take 10 meters, From here it will be 9 meters. And from top, the middle will be at 8 meters. Yes, that's correct. Okay, so there is a correction. I was getting confused in what is happening in the question. There is a correction. This, since the midpoint is starting, let's not talk about the midpoint. We will assume that this clay layer is starting from here. The top clay layer is starting from here. Why? Because you see, in all our equations, we are calculating the delta sigma, and delta sigma is due to this load transfer. Surely there will be a sigma, there will be load here, but there will not be a delta sigma here. Delta sigma is due to this. And when we are calculating the settlement, we write log of something into log of sigma plus delta sigma over sigma. If delta sigma is 0, sigma over sigma will be 1 and the whole thing will become 0. Do you understand my point? At this, due to this clay layer, due to this portion of the clay layer, it does not mean that the load on the pile in this section is 0. It does not mean that. There is, because we calculate the stresses, uh, if you remember, in the when we calculate the pile capacity. What we mean to say here is that the delta sigma due to uh, pile load will be 0 here, because the delta sigma is due to this portion. And our formula for settlement is Cc by 1 plus E naught H over log of sigma plus delta sigma over sigma. If delta sigma is 0, this becomes log 1, which equals to 0, and this whole term becomes 0. So we will ignore this part and we will assume that this clay layer is starting from here, and the midpoint will be 7 by 2, it will be 3.5. Okay, so let's proceed with the question. I hope this is clear. So let me this will be somewhere here. Change the color for this. Okay, so this is the portion that we are examining now. This is the portion that we are examining now. So Z1 is 7 by 2, Z2 is 7 plus 4 by 2, which will be equal to 9, and Z3 equals 7 plus 4 plus 2 by 2, which will be equal to 12 meters. So we got these values. Now delta sigma 1 will be equivalent to, we know delta sigma equals Qg over Lg plus Z Bg plus Z. So delta sigma 1 will be equal to 2000 over 3.3 plus 3.5 into 2.2 plus 3.5. Delta sigma 2 will be equivalent to 2000 over 3.3 plus 9, 2.2 plus 9, and our delta sigma 3 will be equal to 2000 over 2.2 plus 12, 3.3 plus 12. Okay, let's calculate this. So our delta sigma 1 equals 51.6 kilonewton per meter square. Delta sigma 2 equals 14.52, and delta sigma 3 equals okay. So now we need the sigma 1, sigma 2, sigma 3. Let me actually copy this. Okay. So sigma 1 will be equal to, is there a groundwater? Yes. 2 into this.